Imagine rubbing a sheet of paper against solid steel and watching the steel lose a fight. Sounds impossible, doesn't it? Yet every day, a product thinner than a credit card removes rust from ships, smooths hardwood furniture, shapes aircraft components, and helps build some of the world's most advanced machines. Most people see sandpaper as a simple tool. But what if I told you that it's actually a carefully engineered cutting surface made from minerals nearly as hard as diamonds? Think about this. A single sheet of premium sandpaper contains millions of microscopic cutting edges. Each tiny grain acts like a miniature blade designed to shave away material with astonishing precision. You hear the scratch, feel the vibration, and watch dust appear, but you never see the incredible engineering hidden beneath your fingertips. And this is where it gets truly extraordinary. Today, we're following the complete journey of sandpaper. From mineral mines and chemical plants to high-speed coating lines and precision inspection systems. You'll discover why some abrasive materials can cut steel, titanium, and even aerospace alloys. And you'll see how factories manufacture millions of sheets every day with accuracy measured in microns. What happens next surprised even experienced engineers when modern abrasive technology transformed an ordinary workshop tool into a precision industrial product. Because before sandpaper can smooth wood or polish metal, its story begins deep underground inside some of the world's largest mining operations. Most premium sandpaper starts with abrasive minerals such as aluminum oxide, silicon carbide, garnet, zirconia alumina, or ceramic abrasives. These materials originate from countries including Australia, China, India, South Africa, Brazil, and the United States. Some of these minerals rank among the hardest materials used in industrial manufacturing. Their entire purpose is simple: wear down everything else before they wear down themselves. Aluminum oxide, one of the most common abrasives, often begins as bauxite or mined in Australia, Guinea, Brazil, and India. Massive excavators remove millions of tons of material each year. Refineries then process the ore into purified alumina before converting it into abrasive-grade aluminum oxide. Most people never think about this, but a simple sanding disc may trace its origins back through multiple continents. Silicon carbide follows a completely different path. Manufacturers combine silica sand and carbon inside electric resistance furnaces operating near 2,200 degrees Celsius, or nearly 4,000 degrees Fahrenheit. The reaction creates incredibly hard crystalline structures capable of cutting glass, ceramics, and hardened metals. The glow from these furnaces resembles a miniature artificial sun. But here's what nobody tells you. The abrasive grain itself represents only part of the product. Manufacturers also need specialized paper, cloth, polyester film, synthetic resins, and backing materials. Some backing papers undergo multiple strengthening treatments because they must survive tremendous mechanical stress during sanding. The supply chain stretches across thousands of miles. Abrasive grains travel by ship, rail, and truck before reaching manufacturing facilities. Delays in ports or transportation networks can disrupt production schedules, affecting millions of finished products. What appears to be a simple sheet of sandpaper often represents one of the most globally connected products in a workshop. Environmental impact remains a growing concern throughout the abrasive industry. Mining operations consume land and resources, while manufacturing requires significant energy. Modern producers increasingly invest in recycling systems, cleaner production technologies, and waste reduction programs. The goal is to create stronger abrasives while reducing their environmental footprint. Before production begins, manufacturers carefully sort abrasive grains by size. Some particles measure hundreds of microns across, while finishing grades may use grains barely visible to the naked eye. Precision screening equipment separates billions of particles into exact categories, because the next stage demands a level of accuracy most people would never believe. Now the real transformation begins. Raw minerals, industrial resins, and backing materials are about to enter a manufacturing process where electricity, chemistry, heat, and automation combine to create one of the most effective cutting tools ever invented. And the first step looks more like a science experiment than a factory operation. The manufacturing process begins with the backing material. Giant rolls of paper, cloth, polyester film, or fiber backing unwind to production line at speeds reaching 100 meters per minute. Workers monitor tension systems carefully because even a slight wrinkle can ruin thousands of meters of product. Think about this. Before a single abrasive grain touches the surface, the foundation must already be nearly perfect. Next comes a make coat, the first adhesive layer. Precision rollers spread synthetic resin evenly across the moving backing material. The coating thickness often measures just a few thousandths of a millimeter, yet it determines how securely the abrasive grains will bond. What happens next surprised even experienced engineers when they first saw it in action. And this is where it gets truly extraordinary. Instead of simply sprinkling abrasive grains onto the adhesive, many factories use electrostatic coating systems. Powerful electric fields charge the abrasive particles and cause them to stand upright like tiny soldiers. This means the sharpest cutting edges point away from the backing, dramatically improving performance. Imagine billions of microscopic cutting tools landing in exactly the correct orientation. The electric field guides each particle toward the adhesive surface with incredible precision. Without this process, the sandpaper would cut less efficiently and wear out much faster. Most people never think about this hidden layer of engineering every time they sand a piece of wood. Once the grains settle into place, the product enters the sizing stage. Another layer of resin called the size coat flows over the abrasive surface. This second coating strengthens a bond and helps distribute grinding forces during use. Depending on the product type, manufacturers may add grinding aids, anti-loading compounds, or heat-resistant additives at this stage. Now comes one of the most critical stages in the entire process. The coated material enters massive curing ovens stretching dozens of meters in length. Temperatures typically range from 90 degrees Celsius to 130 degrees Celsius, or 194 degrees Fahrenheit, to 266 degrees Fahrenheit, depending on the resin chemistry. Over several hours, controlled heat hardens the adhesives and locks billions of abrasive particles permanently into position. Inside the curing section, sensors constantly monitor temperature, humidity, airflow, and conveyor speed. If conditions drift even slightly outside specification, product quality can suffer. Workers and automated systems collaborate to maintain perfect process control. Because once the resin cures incorrectly, there is no easy way to fix it. After curing, the material cools before moving into converting operations. Giant cutting machines slice the continuous rolls into sheets, discs, belts, and custom industrial shapes. Precision blades operate at remarkable speeds while maintaining tolerances measured in fractions of a millimeter. The factory floor fills with the rhythmic sounds of automated cutting systems. For sanding belts, manufacturers join the ends using specialized splicing systems. These joints must survive tremendous forces during operation. Industrial belt sanders can run at speeds exceeding 30 meters per second. At those speeds, even a tiny weakness could destroy the belt instantly. Some premium abrasive products receive additional treatments after curing. Manufacturers may apply stearate coatings to reduce clogging or specialized ceramic technologies to improve cutting performance. These advanced formulations allow sandpaper to work longer, cut faster, and generate less heat during operation. By this point, the product already looks finished, but hidden defects can still remain. Improper grain distribution, weak bonding, coating inconsistencies, or microscopic contamination could affect performance. That's why the next stage combines artificial intelligence, lasers, sensors, and human expertise to inspect every detail before a single sheet reaches a customer. At first glance, sandpaper may seem too simple to require advanced technology. But the reality inside a modern abrasive factory looks more like a semiconductor plant than a traditional workshop. High-speed cameras, laser scanners, artificial intelligence systems, and precision sensors monitor production 24 hours a day. Most people never think about this, but every sheet must meet strict performance standards before it can leave the factory. The first inspection begins with optical scanning systems. Ultra-high-resolution cameras capture thousands of images every second while the abrasive material moves beneath them at production speed. AI software analyzes grain distribution, coating consistency, and surface defects in real time. A missing patch of abrasive only a few millimeters wide can trigger an automatic rejection. Next come the laser measurement stations. These systems measure coating thickness and abrasive height with astonishing precision. Tolerances often fall within plus or minus 20 microns. To put that into perspective, a human hair measures roughly 70 microns thick. The factory is literally measuring features smaller than what your eyes can clearly see. But visual inspection alone isn't enough. Engineers also test bond strength. Specialized machines pull abrasive grains from the back of material using controlled force measurements. If the grains attach too easily, the product fails immediately because a sheet that sheds abrasives during use becomes useless long before its job is finished. What happens next surprised even experienced engineers. Some manufacturers actually build robotic sanding machines that spend their entire existence destroying sandpaper. These automated systems continuously sand wood, steel, aluminum, and composite materials while sensors record wear rates, cutting efficiency and heat generation. The goal is simple: find weaknesses before customers do. Heat management plays a huge role in abrasive performance. During testing, thermal cameras monitor temperatures generated at the sanding surface. Excessive heat can damage both the sandpaper and the workpiece. Engineers study temperature patterns frame by frame, searching for improvements measured in fractions of a second. Factories also perform accelerated aging tests. Samples spend days inside chambers that simulate years of storage and use. High humidity, extreme temperatures, and rapid environmental changes challenge the adhesive bonds. If the resin cracks, weakens, or loses flexibility, the product never reaches a market. The rejection process is surprisingly ruthless. Premium manufacturers may reject 2 to 5% of production before packaging. Even minor coating imperfections, uneven grain spacing, or microscopic contamination can send entire batches back for recycling. The standards remain strict because professionals depend on consistency every single time they sand. And yet, despite all this automation, human skill still beats machines in certain situations. Veteran inspectors can often identify subtle texture differences by touch alone. Years of experience allow them to recognize patterns that software may overlook. Their fingertips become precision instruments developed through decades of practice. Only after passing every inspection does the product move to packaging. Automated systems count, stack, label, and wrap thousands of sheets every hour. Barcodes, traceability data, and production records follow each batch through global distribution networks. Every package carries a hidden history of minerals, chemistry, engineering, and testing. At this point, the sandpaper is ready for workshops, factories, shipyards, aerospace plants, and construction sites around the world. But before we finish this journey, we need to zoom out and see the astonishing scale of the global abrasive industry, because the numbers behind this humble product are far bigger than most people could ever imagine.